All right, in this video we're going to look at some more identities that we haven't explored yet. And so on your sheet, the ones that we're going to be looking at today are the sum and the difference identities. So using these three for sine, cosine, and tangent. So for our notes, so these identities have two purposes. One is so that we can make evaluations using the values from the unit circle, so that we could evaluate maybe what sine of 75 degrees is. That's something that's not on the unit circle, but we could find an exact answer without using a calculator using these identities. The second purpose for using the identities is to do the proofs like we've been doing in class. And so I'm going to show you guys in this video how to not only use them for an evaluation, but also how to use the sum and difference identities to complete a proof. So first we're going to go ahead and talk about evaluating. And so here's our first example. We're going to find the exact value for sine of 23 pi 12ths. Right. So the first thing that I would do in this problem, since we are maybe not the best at adding and subtracting fractions, is for these types of problems, I would actually convert that into degrees just to make sure that I knew what to angles to add or subtract to make this. And so here, if we convert this into degrees, we're going to find that what we're working with is sine of 345 degrees. Okay, so now I have to look at my unit circle and figure out two angles that I could add or subtract to make 345 degrees. So we're going to have some options. We're going to have, maybe we could say sine of 300 degrees plus 45 degrees. We could say that we have sine of 360 degrees minus 15 degrees. Now this, I was thinking of this, but we don't have 15 degrees on our unit circle, so that's silly. Don't write that one, erase that one. Oh goodness. Okay, here's one we could actually use. We could have sine of 120 plus 225. There's gotta be more. Ooh, 315 plus 30. Sine of 315 plus 30. That would work. Sine of 345. So you can have different versions, adding, subtracting, whatever. This one's so big that most of the ones we would probably think of would be adding. But your goal is going to be to find two numbers you could add or subtract to equal that degree measure. And then once you have that, let's go ahead and write out this formula. So what I did is, instead of writing out a formula for addition and a formula for subtraction, I just did one that kind of covers both of them. So since we're using addition here, we're going to use the plus sign, and so we look over here and we use the plus sign. So you can see that the plus sign is on top. So if this is adding, then this is adding. Cos is kind of opposite, where if you're adding to for cos, you're actually subtracting. You can see that because those are the top signs. Okay, so I'm going to go ahead and write this formula out. We have sine of alpha plus beta is sine alpha cos beta plus cos alpha sine beta. And what I have to do is choose what my alpha is going to be and what my beta is going to be. So if I was doing 345 by 300 plus 45, this is the 5 pi thirds, and this would be pi fourths. And if we add those together, we're going to get 23 twelfths. So I'm going to go ahead and write this in radians, just because my assumption is we're a little bit more used to finding radian measurements on the unit circle now. So I'm going to say that this is sine of 5 pi thirds plus pi fourths. which is sine of 5 pi thirds cos of pi fourths plus cos of 5 pi thirds sine of pi fourths. And then we just look at our unit circle. So sine of 5 pi thirds is negative root 3 over 2. Cos of pi fourths is root 2 over 2. Cos of 5 pi fourths is positive 1/2. Sine of pi fourths, sorry, that was 5 pi thirds. Sine of pi fourths is root 2 over 2. And so I'm going to go ahead and write these down. 4 times 4 on the bottom, or sorry, 2 times 2 on the bottom is going to be 4. Negative root 3 times positive root 2 is negative root 6. 1 times root 2 is just root 2. 2 times 2 is 4. And so if we wanted to write our exact answer for this, sorry, I hit that. We're going to say that our common denominator is 4. And for the numerator, we're going to have negative root 6 plus 2. And what you'll notice when you do this assignment is that because the answers on the unit circle are fairly repetitive, the answers for the problems we're going to do are fairly repetitive as well. And so you're going to see mostly root 6s and root 2s and adding and subtracting them and always being over a denominator of 4. You're going to notice that a lot for today for the problems that have sine and cosine. All right, example 2. I want to do a tangent one because the sine and cosine graphs are pretty similar, or not graphs, but equations. The tangent identity is quite a bit different, so we're going to go over those. So we're going to find the exact value of tan of 5 pi twelfths. Again, my first step would probably be converting this into degrees just so I can think about adding and subtracting more easily. So tan 75 degrees. And so let's think of some different options we have. We could do tan of 30 plus 45. We could do, my parentheses are in a weird place. We could do tan of 135 minus 60. That would give us 75. Always lots of different things you can think of that would make that work. So let's go ahead and do a subtraction version with this one. So I'm going to write down my tan formula. Since we are doing a subtraction problem, that means we're using the bottom sign. And so I'm going to use the negative right here and the negative here, and that means I'm going to use the positive right there. So I'm going to go ahead and write down my formula. I have tan of alpha minus beta is tan alpha minus tan beta divided by 1 plus tan alpha tan beta. Okay. So 135 degrees is 3 pi fourths. 60 is pi thirds, and so we'll go ahead and set it up this way. So I'm going to say tan of 3 pi fourths minus pi thirds is tan of 3 pi fourths minus tan of pi thirds divided by 1 plus tan 3 pi fourths times tan of pi thirds. Okay, so tan of 3 pi fourths we know is -1, so I've got -1 minus tan of pi thirds, that is the 0.1/2 root 3 over 2. And so tan of pi thirds would be root 3 over 1. So this is -1 minus root 3 divided by 1 plus -1 times root 3. And so this gives us the answer -1 minus root 3 over 1 minus root 3. And there's our exact answer. Now, technically, this is not a proper answer. They would say you need to rationalize it so you don't leave a radical on the bottom. But what I've learned being an upper level teacher and talking to people that teach calculus in a college setting is that they don't simplify this in college. They just kind of leave it the way it is. And so we are going to leave it that way for now. Since we are learning this quickly, that's going to be the best for us. Okay, I do want to show you a tangent example that's a little bit more difficult. So what I'm going to do is actually take this exact same problem, and we're going to do this version right here, the tan 30 plus tan 45. So exactly the same problem. I'm just going to write it out. Tan 30 is pi 6. Tan 45 is pi 4ths, and I'm going to show you why the problem is a little bit more difficult. Even though we're doing the exact same answer, it's going to be more difficult for us to get there. Okay, so this is a plus, so that means that if I'm looking at my sheet, I'm going to use a plus on top and a minus on the bottom. So I'm going to have tan alpha plus tan beta divided by 1 minus tan alpha times tan beta. Okay, so the reason that this one is going to be a little bit more complicated is because pi 6th is the point 3 over 2, 1 over 2. And so for tan, this would be 1 divided by root 3, which we know is root 3 over 3. So on the top, I have root 3 over 3 plus tan of pi 4ths is 1. Divided by 1 minus root 3 over 3 times 1. Okay, so what's happened here is instead of having just something simple and a radical and simple and a radical and just kind of having this mess, we have like fractions. So what I'm going to do is I'm going to take this 1 and I'm going to write this as 3 over 3. And I'm going to take this one and I'm going to write this as 3 over 3 as well. So what I did is I was getting a common denominator. So on the top, I have root 3 plus 3 over a common denominator of 3 divided by 3 minus root 3 over a common denominator of 3. And so at this point, what I have is a fraction divided by a fraction. I'm going to go ahead and do keep it, change it, flip it. And these cancel. And I end up getting root 3 plus 3 over 3 minus root 3. And I don't have a calculator handy, but if you were to type both of these into a calculator, you would find that they actually give you the same decimal answer, so they're technically the same. And then the same thing as what I said before is that because the numbers on the unit circle are so repetitive, when we do these problems, we're going to find that these answers are also repetitive for tangent. So we're going to find all sorts of 3's and square root 3's in our answers, and we're going to have fractions that look like that each time. Okay. Example 3, sometimes they give you a problem and they just want to know what you were using it to approximate. So if they give you a problem and they say maybe cos 10 degrees, cos 40 degrees, minus sine 10 degrees, sine 40 degrees, and they're asking you what this is being used to approximate, we would just look at our sheet and we would see they wouldn't tell you to look at the sum and the difference, but we'd kind of have to become familiar with them as we worked with them. So this, based on the way it looks, I would say, oh, that's either sine or cos. And if I look at it, I can see that these are both cos and these are both sine, which tells me that this was a cos sum or difference formula. And since I have a minus in the middle, that means that it must have been a plus. So I'm going to go ahead and kind of go backwards here. The alpha is 10 and the beta is 40, and we have a minus here, so that means that it was cos of 10 plus 40. And so this formula represents cos of 50 degrees. Okay, not a super complicated problem, but common enough that we'll see it a few times. Okay, And then, so that's all the evaluating we'll typically do, but I do want to go over a proof with you guys so you can see how that works. These proofs usually, they look kind of nasty because they have two different variables as far as like alpha and beta, but the proofs themselves are usually pretty simple to actually work out. It's usually 2 steps, maybe 3. So the proof that we're going to do as an example is we're going to do sine of alpha plus beta divided by cos alpha cos beta and when I look at this problem, I can see that this is like one big term and this is 2 terms. And normally I would have told you take the side that's 2 terms because it's a little bit easier to like mush those to be 1. And I would say maybe you could still do that route. But in this case, I'm going to work with the left side. Okay, so these ones, I think you can kind of go either way. Sometimes it's most beneficial to figure out where the sum or difference formula is and then substitute something in for that. But I've even noticed some of the problems that doesn't really help. So I would say with this one, just pick a side and work with it. If you get stuck, give up on that side and work with the other side instead, because usually these you should be able to figure out within a couple steps. So this is a sine sum problem, alpha plus beta. So I'm just going to look at my sheet for where we have the sum formulas, sum and difference. Sine of alpha plus beta means I'm going to do sine alpha cos beta plus cos alpha sine beta. So I'm going to go ahead and write that out. All right, and then if you can see, I have like this term plus another term, and then I have that common denominator. So to get this one piece and split it into 2, like what I can see on the right side, I'm gonna go ahead and take this fraction and split it apart, and I'm just gonna make sure that each piece has all of the common denominator. So what I did is I took the first piece, I put it over the common denominator. Now I'm taking the second piece and I'm putting it over the common denominator. I guess I can go ahead and write the right side down. Okay. So now if you see this, your cos betas are the same, so they cancel. Your cos alphas are the same, so they cancel. And I'm left with sine alpha over cos alpha, which is actually tan alpha. And then I have sine beta over cos beta, which is tan beta. And so tan alpha plus tan beta equals tan alpha plus tan beta, and I'm actually done. And I would say typically the problems do seem to work out like that quickly when you're doing these proofs using sum and difference identities at this level. So above calculus and beyond, of course, they'd be more complicated. But for the ones that I'm going to be assigning to you guys, they really will work out that quickly.